Another example for plain truss analysis using the combination of join method and section method. This is somewhat look like Parker truss, and the values of reaction at point A and point E were already computed. So I can see that the join method will be conveniently used to join E, join C, and join A. So for the rest of the members, we can use a section method here and here. So for the joint E, C, and A, I already draw the free body diagram for joint E, for joint C, and for joint A. So let us start with the computation. The value of the slope of member EF is 3 meter horizontal, 3 meter vertical. So therefore we have 1:1 and the square root of 2 and the hypotenuse. So summing up the force along y-axis is equals 0. So going up force should be positive. So therefore this is 7 equals going down force 1 over square root of 2 multiplied by stress of EF. Therefore EF is equals 7 multiplied by square root of 2. That is 9.90 kilonewton. So therefore this is compression force. And for member DE, summation of force along x-axis equals 0. So going to the right should be positive. So 1 over square root of 2 multiplied by EF, which is 9.90, is equals DE. Therefore value of DE is equals over square root of 2. This is 7 kilonewton tension. So put all the computed stresses in the matrix. Member DE is 7 kilonewton tension and EF 9.90 kilonewton compression. Okay, next I will bisect this portion and I will use the right structure for my analysis. So I already draw the free body diagram of the right structures. Okay, so remember that member EF is connecting to the joint F, member GF connecting to the joint F and G. So this horizontal distance is 3 meter. And member DG is connecting joint G and joint B. So the vertical slope will be 4.5 meter by 3 and 3. So this is also should be 2:3 is to square root of 13. And this one for member GF The slope vertical is 1.5 and 3. Therefore, this is 1:2. Therefore, the hypotenuse is square root of 5. So let us put it here in the free body diagram. Okay, so this is the slope of member GF. 1 vertical, 2 horizontal, and for hypotenuse, square root of 5. And for member TG, the slope is 3 vertical, 2 horizontal, square root of 13 for the hypotenuse. So establish all the points where the members are connected. So I draw the line here in order to use the transmissibility of force or to expedite or speed up the computation. So when you say transmissibility of a force, let's say this is a member GF. So let's say it is act as tension force. So this is the axial force of force GF. So because this is slant, it has the component, vertical component, horizontal and vertical. So when you apply the force here at joint F, this is the component. You can apply also the force in joint G. So this is also the application of horizontal and vertical component. This is called FGF because this is the horizontal component. This is 2 over square root of 5, and this is FGF 1 vertical over square root of 5. Okay, that's the transmissibility. So we can transmit also the force at point, let's say this is point O. You can transmit it here. You can transmit it here. You can transmit it here. So in all members, we can do the same in order to eliminate too many forces for the computation. So to avoid the confusion of the signs and rotation of the force. Okay, we can find the distance from point E to O as 3 meters. Because through similar triangle, we can draw the triangle here from point F traversing to this horizontal distance. This is 3 meter. This is 1.5 meter. Okay, because of the drawing, the height of the truss is 4.5 and up to this point is 3 meter. So we have the remaining 1.5 here from F to G vertically. So from this similar triangle, this is 1.5, then horizontal is 3 meter. Then another triangle here, this is 4.5 over, let's say this is X, this is the whole X from C to O. So this is C, this is O. So through similar ratio proportion, this is 4.5 over, for a small triangle, vertical is 1.5. Then for X, horizontal for large triangle over 3. Then X is equivalent to 9. So therefore, if it is 9, and this is 3 plus 3, this is 6, so 9 minus 6, it should be 3 meter. So 3 meter, 3 meter, so 3 meter. The height of D to F is 3 meter. And height from C to G is 4.5 meter. Okay, so this is the expository line or the bisecting line. So I will assume that member FG is act as compression member, and for DG also compression, and for member CD I will assume it as tension member. So we can get the value of either FG, DG, and CD. So if we summing up the summation of the forces at point D, so if the force is concurrent with this point, it has zero moment because it has no moment arm. So 2 is 0 at this point, and CD is 0 at this point, and DG is 0 at this point. So we can put the component of FG at point F or at point O. So let us use the or both the point as the center of moment. Okay, first, summation of moment at point D equals 0. So I will use counterclockwise as positive. So I will put the component of FG to point F. Okay, putting the component of FG at point F. So this will be it's look like this is FG horizontal, that is vertical, that is 1 over square root of 5, and for horizontal this is 2 square root of over square root of 5 FG. Okay, so if it is here, so because the vertical is concurrent to point D, it will be 0 because it has no moment arm. So here is the 2 over square root of 5 FG. So let us proceed. So this is 0, 0, and DG is 0 at this point. So let us first analyze the FG. 2 over square root of 5 FG, moment arm is 3 meter multiplied by 3. So this is counterclockwise towards T multiplied by 3. Then this is clockwise. So we can equate 7 multiplied by 3. Therefore, the force or stress at FG is equals to 7 multiplied by 3, 10 multiplied by square root of 5 over 2 multiplied by 3. Then FG is equals, okay, this will give us 7.83 kilonewton. So therefore the result is positive. This is compression. The assumption is correct. Okay, let us consider to transmit the component of FG at point O. So let us summation of moment at D, still at D. So my convention is for counterclockwise moment, positive. Okay, we should bring it here. This is the 1 over square root of 5 FG. and this is the 2 over square root of 5 Fg. So because the horizontal component is concurrent with the point D, so this has no moment arm, so this is 0. So the existing force is the vertical component and 7, and since this is also concurrent, this is 0 and CD is 0. Okay, so 1 over 5 square root of 5 Fg multiplied by 6 as moment arm equals 7 multiplied by 3. Then Fg is equals, okay, we get the same answer, 7.83 kilonewton compression. Okay, let us find the value of the other forces, other members, DG and CD. So this time I will place my summation of moment at point G. So because Fg is concurrent with this point and DG is concurrent with this point, so I will solve the value of CD. The moment arm is 4.5 and 2, the moment arm is 3, and I have reaction of 7, moment arm of 6. So summation of moment at point G equals 0, counterclockwise moment, positive, counterclockwise. So CD is counterclockwise, multiplied by moment arm na 4.5 plus 2 counterclockwise multiplied by 3 moment arm, then clockwise 7 equals 7 multiplied by 6. CD is equals 7 times 6 minus 2 times 3 over 4.5. This is 8 kilonewton. So I have the result or positive result. This is tension. The assumption is correct. So what we leave here is the value of TG. So through summation of vertical or horizontal forces, we can get the value of DG. Okay, let me solve it here. Value of DG, summation of force horizontal, are here. Summation of force horizontal equals 0, so going to the right forces should be positive. So the horizontal component of DG is going to the right, horizontal. So we have slope of horizontal, that is 2, and the hypotenuse is square root of 13. This is component of DG. The other forces going to the right is the component of FG. The horizontal component of FG is 2 over square root of 5. The value of Fg as computed is 7.83. So this should be multiplied by 7.83. So what else? So we have the value of CD going to the left. So this is minus 8 kilonewton equals to 0. Therefore, value of DG is equals So through calculator, this is 1.80 kilonewton. So compression. Or for finding dg, we can also use summation of moment at point O. So let us try. So summation of moment at point O equals 0. So counterclockwise moment positive. So if I put the, okay, so concurrent Fg, so this is 0. Concurrent, another concurrent force is CD. So this is 0. I will put the component of DG to point B. So this is the horizontal component for DG, that is 3 over square root of 13 DG. So because this is concurrent towards O, so this is 0. But the vertical component is 3 over square root of 13 dg. So we have two vertical forces here, the 2 kilonewton and the component of dg, and also at point E 7. So CD is 0. Okay, so 7 multiplied by 3 meter up to point O multiplied by 3. So counterclockwise. Then clockwise is 2 meter and the component of dg. So let us put it to the other side of the equation. 2 multiplied by 6 plus 3 over square root of 13 dg. dg is equals, we should get the same answer as 1.80. Okay, put the momentum of the vertical component multiplied by 6. So when you computed it, it will give us the same answer as 1.80 kilonewton. It's compression. So what I'm trying to emphasize here, that you must choose the point where you can eliminate as many or forces that can eliminate, so you can lessen the computation in order to avoid the confusion. Okay, from the computation, I get the value of Fg as 7.83 kilonewton compression, and value of dg is 1.80 kilonewton compression, and CD, which is 8 kilonewton tension. Okay, knowing the value of CD, I can proceed to point C. We just get here point CD as 8 kilonewton. Okay, this is tension, 8 kilonewton tension. Okay, therefore the value of BC is also the value of CD, which is 8 kilonewton. So this is 8 kilonewton, and the value of CG is 8 kilonewton tension. So the value of CG is 8 kilonewton tension, and value of BC is also 8 kilonewton tension. So I can proceed now to using the section method again to get the value of member HG and member PG. So this member is already computed, so I will traverse the line here and draw the free body diagram, and I will get the left portion of the structure. So I already draw the free body diagram of the left structure. So knowing that BC is tension and has the value of 8 kilonewton, so I will try to get the value of GH and BG. So again, through the transmissibility principle, okay, we can sum up the moment at point B. Okay, assuming that BG is compression and GH is compression, so if I sum the moment at BG, so because this is concurrent, BG is 0 here, BC is 0, and this 6 is 0. So I will put the component of GH here. So the vertical component of GH is 0 because it is concurrent with this point. So what is left is the horizontal component. So horizontal component is the same with the slope of the previous. Okay. Similar with the previous free body diagram of the slope. Okay, summation of moment at B equals 0. So all the counterclockwise moment should be positive. So here, this is 9 counterclockwise, so 9 multiplied by 3. Then another is horizontal component of GH. So this is clockwise, so I will put it to the other side of the equation. GH, the slope is 2 over square root of 5 multiplied by 3 meter. So 3, this is 3, GH will be equivalent to 9 multiplied by square root of 5 over 2. This is 10 kilonewton. So we get the positive result. This is compression. Okay, so but because BG is the only one left that the stress should be still determined, so we can use the summation of force along x-axis or summation of forces along y-axis. So let us use the summation of force along y-axis equals 0. So this is going down force, the component of BG. Use the slope 3 for vertical over square root of 13 multiplied by BG. That is horizontal. So this is going down. So what is another going down is 6 kilonewton here. Then another going down is GH plus 1 over square root of 5. The value of G is, as computed, is 10. So equals 9 kilonewton. That's the only going up force. So the value of BG is equals. So the result is negative 1.77 kilonewtons since it is negative. So the member BG is not compression but instead it is tension. Kilonewton, BG is tension. Okay. So put all the computed value here. So GH and BG. BG is 1.77 kilonewton tension, and for GH is 1.77, GH 10 kilonewton. Compression. Let us proceed to joint A. So since BC, we get BC as tension, which is 8 kilonewton. We can get the value of AH. So either summation of force horizontal or force vertical. So this time, use the summation of force along y-axis or vertical. That is 1 over square root of 2 AH should be equals to 9. AH is equals 9 multiplied by square root of 2, which is equivalent to 12.73 kilonewton. So this is compression AH. 12.73 kilonewton compression. So what is left is AB is also 8 kilonewton tension. What is left is BH. So this vertical member and this vertical member. So by joint through H and F, we can get the value of vertical member. Okay, free body diagram of joint H. So we have here AH as compression. The computed value of AH is 12.73, and this one GH, the computed value for GH is 10 kilonewton compression, 10 kilonewton. So this, I will assume it as compression also. This is BH. So either through vertical force or horizontal or vertical force. Okay, summation of forces along y-axis. So BH positive should be going up, should be positive. BH plus this one, this is 1 over square root of 2 multiplied by 12.73. Equals 10 so the slope of GH is 1 over square root of 5. So member BH is equals, so this is negative 4.53 kilonewton. So therefore, this is tension. BH is equals 4.53 kilonewton tension. This is 4.53 kilonewton tension. So for the joint F, GF is compression. It has the value of 7.83 kilonewton Let's assume again this is compression dF, and the value of EF is 9.90. Compression 9.90. The slope is 1:1, square root of 2, and the slope of this is 1:2, square root of 5. So summation of force vertical equals 0. So dF plus 1 over square root of 2 multiplied by 9.90 equals going down force na 7.83 multiplied by 1 over square root of 5. So dF is equals, so the result is negative 3.5 kilonewton. So therefore dF is equals 3.5 kilonewton. This is tension. Okay, so we already completed the stresses in all members. 3.5 kilonewton tension.